Whenever we send information from one computer to another, there's always a risk that the signals received are going to be interpreted differently from the message that's being sent. In this case, I'm sending a message from one Arduino to another. This is the transmitter, and this one here is the receiver. And they're communicating using just a basic clock and data protocol that looks something like this. You can see the clock is pulsing here, and it's just going from high to low. And then each time the clock goes from low to high, the receiver looks at the data signal and interprets it as either a 0 or a 1. But I've also got this switch in the middle here that I can press to interfere with the data line. And so if I do that, we get the wrong thing here on the receiver. So now I know I'm using this switch to artificially cause problems, but it's because it's possible for this sort of glitch to happen all on its own. So I'm showing these as nice, clean on-off signals, but really everything is analog. These are just voltages, and there's any number of reasons that occasionally this voltage might not be quite high enough to register as a 1, or this voltage might not be quite low enough to register as a 0. Without a lot of extra engineering work, any circuit's going to be susceptible to some sort of electromagnetic interference. For example, if I run the power cord for my lights nearby the circuit, occasionally I can cause problems just by flicking the lights on and off. The quickly changing current in the power cord causes a changing magnetic field that might induce unwanted electrical currents in the nearby electronics. So, okay, if we accept that errors are going to happen, what can we do about it? How can a computer that's receiving a signal that, as far as it knows, is just a series of ones and zeros, how can it know that the data it's receiving is the correct data? Well, one approach would be to just send the message multiple times. So, okay, we received this message here, and it says, hello world. And maybe that's right, maybe not. So let's try again and see what happens. So reset these and send the message again. And I'll just speed this up. Okay, so now we've got something different. This time it says hello world. So it actually tells us something useful. That tells us that either the first message, hello word, was wrong, or this message, hello world, is wrong. It could still be that both messages were wrong, but we definitely know at least one of them was wrong. So let's try a third time. Reset this and resend the message. And again, I'll speed this up. And now we've got hello world again. So that certainly suggests that hello world is likely to be the right message. So in terms of, figuring out if there was an error in our transmission, I don't know how you feel about that. It doesn't seem all that efficient to me. I mean, we've got to send at least twice as much data. So we've got to send the message twice and at least twice to see if it's the same. But it does look like it works pretty well. I mean, as long as we don't get the exact same error in the exact same place, this ought to catch pretty much any problem. So hey, it works, and maybe that's good enough. But it really is not that efficient because we've got to send the message at least twice. So let's try to do better. Well, if we don't send the message multiple times to verify it, what else could you do to figure out that this is wrong? What if I told you the message is supposed to be a normal English sentence? Well, obviously, if you knew that, then it's clear that there was an error since this isn't an English word. So that might suggest that maybe we don't actually have to send the exact message multiple times to verify it. It might be good enough just to send the message along with some sort of description like, hey, this is supposed to be English. That would give you enough information to know that some bits must have changed along the way. So what sort of description could we send along with the message? Literally saying it's supposed to be English only works if you've got some way to understand English. And building a circuit to do that would be very complicated. Even I don't have enough breadboards to do that. So let's actually look at the underlying binary representation of the message, since that's going to be easier to build a circuit to work with. So of course our message, hello world, is really just sent as a series of ones and zeros. And just like knowing the message is supposed to be English can help you spot an error, there are all sorts of ways we could describe the strings of ones and zeros that might help us spot an error. For example, there are 104 bits, and that might be useful to know for detecting certain errors. If we receive more or fewer than 104 bits, then we know that there was a problem. We could say that 47% of the bits are ones and 53% are zeros. Or we could say the longest run of zeros is 6 zeros. And I'm sure you can imagine all sorts of other descriptions that may or may not be useful in figuring out if we receive the message correctly. But of course, some things are better than others. If I said, here's a message and the longest run of zeros is 6 zeros, an error in this bit would be easy to catch. But you could change almost any other bit in the entire message and it would still not have a run of zeros longer than 6. So maybe that's not a useful description. But if I said, here's a message and there's supposed to be 49 ones, well then, any single bit got flipped by accident, there wouldn't be 49 ones anymore, and you know right away that the message was corrupted. Now, it's still not perfect. If this bit gets flipped from a 1 to a 0, and then this bit flips from a 0 to a 1, there's still 49 ones, so you wouldn't catch those errors. But maybe we happen to know that errors are actually very rare and usually only affect a single bit at a time. So if we know that, then if you know how many ones there are supposed to be and any single bit gets changed, then we're guaranteed to catch it. Although as long as we're making that assumption, we don't even need to know the exact number of ones. It's actually good enough just to know that there are an odd number of ones. Because if we're only expecting a single bit to change, if any single bit changes, then the receiver would get a message with an extra one or a missing one, and so the number of ones wouldn't be odd anymore. Now, mathematicians have a fancy word for talking about whether a number is even or odd. They use the word parity. And that word is also used in computer science to describe whether some data has an even or odd number of ones in it. So in other words, we could say that our message, hello world, has odd parity because it has an odd number of ones in the binary representation. Now, the nice thing about parity is that it's either even or odd. There are only two options, so we can keep track of parity in hardware using a single bit. Now, a good way to store a single bit is with a D flip-flop. Now, I've got another video on D flip-flops if you want to know exactly how it works, but basically the D flip-flop can store a single bit that you can read on the output here, and it will update that stored value on the rising edge of a clock to whatever bit is on the input here. So, okay, how can we use this to compute the parity of our message? Well, conveniently, we have a clock coming from our transmitter that's going to give us a rising edge for each bit that's sent. So if we connected that clock to the clock for our D flip-flop, let's just say we connect the output of the flip-flop then back to its input like this. Well, then each clock cycle, we're just going to take whatever's in the flip-flop and put it back in the flip-flop. So in other words, it'll do nothing, which is not very exciting. But now let's put in an XOR gate in here like this. And if you imagine here that this data input is low, then the output of the XOR gate here is going to be whatever this other input is. And so that's going to work just like before. Every time we get the clock, it's just going to put the same thing back in here. So it's still not very exciting. But if the data is high, then the output of the XOR gate is going to be the opposite of whatever the other input is. So if this data input is high, then the flip-flop will alternate each time the clock pulses. So what happens if we hook this up to our clock and data signals? So let's walk through it. Well, if the flip-flop starts off reset and the data is low, then it'll just stay off each time the clock pulses. But here, where the data is high, then on this clock pulse, then we'll invert the output and feed it back in. And so now the flip-flop's output will be high. And then when the data signal goes low again, then each of these clock pulses here, we'll just feed that one back into the flip-flop and it'll stay high. But then when we send another one, we'll invert the input into the flip-flop again, and it'll go low. So in other words, every time we transmit a 1, the flip-flop will alternate states. Or in other words, if the flip-flop starts out off, then if we send an odd number of 1s, it'll end up on, and if we send an even number of 1s, it'll end up off. So if we feed our message into this circuit using our clock and data signals, it should compute the parity for us. So let's give it a try. So to build this circuit, we just need a D flip-flop and an XOR gate. And for the D flip-flops, there's lots of different chips you could use. I'm going to use the 74HC273, but there are a lot of other things you could use. Anything with a D flip-flop will probably be fine. This one has 8 D flip-flops, but we'll just be using one of them for now. So I've got the 74HC273, and then for the XOR gate, I'll use the 74HC86, which is a quad XOR gate. So there's actually 4 XOR gates, and again, we're only going to use one of them for now. And again, even though I'm using the 74HC family, you can use 74LS or whatever you've got. Really any D flip-flop and XOR gate ought to be fine for this. So the first thing I'll do is hook up power and ground for each of these chips. So if we look at the datasheet for the 74HC273, we're only interested in this one flip-flop down here. We've got our input and output on pins 3 and 2, and then we've got the clock, and that goes up to pin 11, and then this clear signal, which goes down to pin 1 here. And the way this works is that bringing pin 1 low resets the flip-flop to 0 regardless of the other inputs. And so we don't normally want it to be resetting itself, so we don't normally want pin 1 to be low. So what I'll do is tie it high through a 100K resistor. The way this pin works is there won't be any current flowing, so there's no current flowing through the resistor, so both sides of the resistor will be at 5 volts, which means pin 1 will be high. But if I want to manually reset it, I can just use a jumper like this and connect pin 1 to ground, and that'll reset it. And having the resistor here will just keep us from having a short circuit when I do that. So that's the clear pin, then pin 3 is the input. And if we look at our circuit diagram, the input comes from the output of the XOR gate. And if we look at the XOR gate, the output of the XOR gate is also on pin 3. So really we just want to tie pin 3 of the XOR gate to pin 3 of the flip-flop. And that will connect the output of the XOR gate to the input of the flip-flop. And we also want the output of the flip-flop to go back around to one of the inputs of the XOR gate. So I'll tie pin 2 to pin 2, and pin 2 is the output of the flip-flop, and that will go to pin 2, which is one of the inputs of the XOR gate. And we also want to see what the output's doing, so I'll hook an LED up to that as well. And I'll connect the other side of the LED to ground through this resistor. And this is just a 270 ohm resistor. Anything that's a few hundred ohms ought to be fine just to limit the current through the LED. And so now we basically got this circuit built, we just need to hook up our inputs. So let me connect the breadboards together here for a transmitter. And the transmit clock was on pin D2 of the Arduino. So I'll hook D2 here up to pin 11 on the 74HC273, which is the clock input of the flip-flop. So there's our clock. And then the transmit data is on pin D3. So I'll hook that up to the first input on our XOR gate here. So what that'll do is every time we send a bit, the clock will pulse, which means every time we send a bit, we're going to load a new value into our flip-flop here. And that value is either going to be the value that's currently in the flip-flop if the bit we're sending is a 0, or it's going to be the opposite of what was in the flip-flop if the bit we're sending was a 1. So in other words, every time we send a 1 bit, the value in the flip-flop will alternate, keeping track of the parity. So that is whether we've sent an even or odd number of bits that are 1s. So let's power this up and see if it works. And there it goes, and looks like it's not working. I would expect to see this start to alternate. Oh, you know what? I forgot to connect the power. So I didn't connect the power between the two breadboards. So let me just do that. So now we're actually sharing power between both of these breadboards, so let's try this again, power it up and see if it works. And there it goes, and now we see it alternating. So every time we send a 1, we should see this LED alternate. And so if you remember before, we looked at the message hello world and determined that it has 49 ones, which means there's an odd number of ones, which means that by the time this is done sending, because 49 is odd, we should expect to see this LED on. And there it goes. So it's done sending the message and the LED is on. So that indicates that indeed, when we sent the message, we had an odd number of 1 bits. So that's great that we can compute the parity on the transmitter. Now, to help us detect if there was an error sending the message, we could do the same thing on the receiver side. In other words, we could duplicate essentially this same circuit over here on the receiver, and then we'd be computing the parity of the sent message and computing the parity of the received message. And then if any single bit gets flipped, 0 changes to a 1 or 1 changes to a 0, between the transmitter and receiver, possibly due to this evil little button I've installed here, then the parity won't match and we'll know that there was an error. So let's build the same circuit over here on the receiver side. And it's going to be identical. We've got a 74HC86 for the XOR gates and a 74HC273 for the D flip-flop. And I'll hook up power and ground to everything. And this time I won't forget to connect power between the breadboards. I'll tie the reset line high through a 100K resistor. The output of the XOR gate will go to the input of the D flip-flop. And the output of the D flip-flop will go back to one of the inputs of the XOR gate. I'll also hook the output of the D flip-flop to an LED and connect the other side of the LED to a ground through a 270 ohm resistor. Then I'll hook the received clock to the clock input of the D flip-flop and hook the received data up to the other input of the XOR gate. All right, so now let's power up our receiver. And so this is where I want to be able to reset the parity bit. So I'll manually connect ground to pin 1 and that should reset it. So now if I reset the transmitter so it resends the message, we should see the parity getting computed on both ends. And if there are no errors, then it ought to compute the same parity. And indeed, it looks like it came to the same answer. So after sending the message over here, we've sent an odd number of 1s. And after receiving the message over here, we've received an odd number of 1s. So now let's reset everything and try introducing an error. So first I'll reset the parity bits by briefly connecting pin 1 to ground. Then I'll reset the receiver. And now reset the transmitter to resend the message. So now let me try to introduce an error. And already you can see the parity bit is out of sync. And so if we just speed this up so it finishes up. And so now at the end of the message, we can see the transmitter thinks it sent an odd number of 1s because the parity bit is on, but the receiver thinks it received an even number of 1s because the parity bit is off. So that means there was definitely an error, and this message here, hello world, is apparently not what we sent. So this is all great, but there's still a missing piece. So if we just focus on the receiver, let's say we receive something like this. We've got this message, hello world, and our parity computation is 0, saying we received an even number of 1s. So the question is, did we receive the message correctly? Well, you might think it looks fishy because we know from before that our message had an odd number of 1 bits, so maybe you'd expect this parity bit to be set. But the message here is actually different. Before the message was hello, comma, world, and now there's no comma between hello and world. And it turns out the binary representation of a comma has 3 1s, which is an odd number, so we would expect a message that's missing a comma to have a different parity from the same message with a comma. So does that mean we received this message correctly? Well, from the receiver's perspective, there's still no way to tell. But if I show you the parity bit computed by the transmitter, I bet you can tell now. Now, since the parity of the transmitted message doesn't match the parity of the received message, then we can't possibly have received the correct message. But of course, you couldn't know that without knowing what parity the transmitter computed. So the only way this is going to be useful is if the transmitter is able to send its parity bit to the receiver somehow, so the receiver can compare it with its own computation. So how do we get the value of this parity bit sent over to the receiver? Well, I think the easiest way is to have the Arduino just read the value of the parity bit and send it the same way it sends the rest of the message. So to get the Arduino to read the parity bit, we can hook the parity bit to an unused data pin on the Arduino. So I'll connect the parity bit, which is the output of the D flip-flop here, to pin D10 on the Arduino. Then in the code for our transmitter, I'll define a new pin for our parity bit on pin 10. And if any of this doesn't make sense, I wrote all this code in my previous video, so check that out if you haven't seen it. In the setup, I'll set the pin mode to input since the parity bit will be read in to the Arduino from the circuit we just built. And then at the end of the loop here, after we're done transmitting our message, we want to transmit the parity bit. So we'll do a digital write to our transmit data line, and instead of saying high or low, we just want to write whatever the parity bit is. So this digital read will read whatever the parity bit is set to, and then put that same value out on our transmit data line. So this works just the same way as when we're transmitting the bits of our message up here in the loop. And then in the same way, we want to pulse the clock high and low to signal that we're sending another bit. So after the loop where we send the message, we put the value of our parity bit out on the data line, and then we have a delay, and then we pulse the clock high, then a delay, and then pulse the clock low again. So after sending our message, we're sending just one more bit, which is our parity bit. So let's reprogram the transmitter with this and give it a try. Connect a USB here. Make sure I'm on the right port. And upload it. And there it goes. Looks like it's programmed, and now it just reset itself. We'll just let this run for now because we have to kind of reset everything else before we can really test it. Okay, so this is programmed and it just reset itself. And so I'll just go ahead and disconnect the USB and get everything else reset. So of course we want to make sure our parity bits are all set to 0 when we start. Reset our receiver. And then we'll reset the transmitter now and let it transmit the message and hopefully also the parity bit. So now it's sending the message just like before. And for now, I won't induce any errors. I'll just let it transmit the whole message. And I'll speed it up a little bit here. Okay, now it's done. And you'll notice right away that both of the parity LEDs on both sides are off. So that suggests that we must have sent an even number of 1 bits and received an even number of 1 bits. And of course, our message hasn't changed. It still has an odd number of 1 bits. But now we've also sent the parity bit, which remember was a 1. And that's actually this one here that you can see on our receiver. But of course, our parity computing circuit is very simplistic. It doesn't know the difference between the data bits and this parity bit. And so it just wound up counting another bit, and we wound up with an even number of 1s. But actually, if you think about it, this leads to an interesting property. Anytime our message has an odd number of 1s, we'll tack on a parity bit that gets us to an even number of 1s. And anytime our message has an even number of 1s, well, then the parity bit will be a 0, so we'll still send an even number of 1s. So in other words, no matter what message we send, the transmitter is always going to transmit an even number of 1s when you count in the parity bit. And so it's actually a name for that when you have when you're always going to transmit an even number of 1s when you add a parity bit, and that's called even parity. And so we can actually describe our transmitter now as having this property of transmitting even parity. So that's actually really convenient. So let's take a look at the receiver again as we receive a message. Now again, we've got this message where we received hello world without a comma. So was that a mistake or not? Well, because this LED is on, we know we received an odd number of 1s. But now we also know that our transmitter has even parity. So counting the parity bit, the transmitter will always transmit an even number of 1s. And so anytime we receive an odd number of 1s like this, and this LED is on after we're receiving, we know that there must have been an error. Because the only way we could possibly receive an odd number of 1s is if some bit got changed along the way after it left the transmitter. Either a bit in our message or the parity bit itself. Now, as I mentioned before, this obviously isn't perfect. If a single bit in our message gets changed, 1 changes to a 0 or a 0 changes to a 1, then that'll change the parity of the message we receive and we'll detect that as a parity error. But if 2 bits change, for example, this 0 changes to a 1, but then this 1 over here changes to a 0, then the overall parity of the message won't change. So in that case, we'll receive a corrupted message, but we won't be able to detect it. So it's not perfect. There's some things we can do to improve the situation. For example, instead of having 1 parity bit for the entire message, we could send a parity bit after every byte. That would help us catch some of these cases where more than 1 bit gets corrupted. But even that won't catch 2 errors in the same byte. And we could keep playing this game and send a parity bit for every 4 bits or for every 2 bits. If we take it to the extreme and send a parity bit for every data bit, then we're basically right back where we started, sending our entire message twice. So it looks like there's this trade-off between improving our chance of catching errors versus sending fewer bits. And indeed, that is a trade-off that you have to make as an engineer designing a system like this. But even so, there are times when you want the best of both worlds. You want to detect multiple errors close together, and you want to minimize the number of extra bits you have to send. So what then? Well, there are more complex techniques for error detection that can get you closer to having the best of both worlds. And that's what I'll talk about in the next video. So please consider subscribing so you don't miss it.